audio there. Let's see. Okay, we run over to, or somehow get to, chapter 15. What we find out is what we talked about the other day, this momentum term, and we figured out this linear impulse. Now we move to a group of particles. Okay, well, we move to a group of particles in the next section. This one, to a group of particles. And we get ourselves all the way down to particular. Let's just do a problem. Okay, let the projector come up. We will put this on, and we will remember that a portion of the screen is unusable. Right here. Okay, we have no marker. Up here, up, all the way across to about right there. And let's drop this out of the way. Let's create or bring up a, nope, wrong window. Bring up the File Explorer. We can move it over to here. This will give us the necessary space to do the problem on the right. All right, so let's work this problem. Says freight cars A and B have a mass of, hang on a second, temperature in here is too high. Twenty megagrams and 15 megagrams. So this is 20 and 15. Determine the collisions if the cars collide and rebound such that B moves to the right with a speed of 2. So since he's labeling A and B, this is what we're going to do. So MA initial, VA initial plus MB initial. Now this is, you look back at the text, the I's here are not, they're AB's. So you're summing on the A and B's here. The B initial goes to mass A final, initial being before the collision, final being after. MA final plus MB final, BA final. So let's look at the necessaries. Now I'm going to keep them in the 20 because it would make no difference since the units are the same. I'm going to use 20 and 15. And they didn't change weight or mass because of the collision. We have that, okay, so we have this one moves to the right. Now here's the key. There is a positive, negative connotation when it comes to velocities. To the right being positive, the left being negative, or if you want to flip them, it doesn't really matter. You have to keep up with what's positive and what's negative. So you see a 3 for A. You see a negative 1.5 for B. He tells you that B moves to the right with a speed of 2. It rebounds such that B moves to the right. This would be B moving to the right with a speed of 2. Here's your B. To the right. The only thing you don't know, he wants to know determine the velocity of A after the collision. That would be this one. So what you got is 20 times 3, or 60. 15, and then half of 15 is 7.5. So I'm going to do this. This is weird. So I'll multiply 1 times 15. I just carried it that way. You take this, 2/15, move it to the other side, and then you divide that by 20. And let me find the solution here. Double click and make sure, let me make sure I'm getting audio on the stream. think I'm getting audio on the stream. There it is. Oh, that's right. I was going to figure this out with a calculator. Okay. I'm 0.375. We can check the answer in the back of the book in a second. Now it says, this is an interesting thing. If A and B are in contact for 0.5 seconds, find the average impulse force which acts between them. Okay. Let's first say the system includes A and B. Okay, so let's list a few facts. One, system includes A and B. During impact, there is no external forces applied to, I'll say this, the AB system. And then I'll say this will be, however, if we redefine, that's misspelled, the system to only A, what happens? We're just gonna, we can pick either A or B, so I'm gonna pick, I gotta pick one. I think I'll pick B. Okay, so let's look at this for a second. What happens to B by itself? Here's B. B comes in, it's moving 1.5 meters a second. When it gets done, it's moving 2 meters a second. That way. So this is B, and this is B. There is A over here, but now the system is redefined so that it only includes B. This means, in order for this to happen now, we know that A did this to B, but the key is, now we've removed A from the system. And if you look at it back the last chapter, we had this. We had sum of the forces equals to dmv dt. We moved the dt over. Then we integrated it, and we had the sum of the forces dt equals to, and we had mv final, mv initial. So what we had is mv final minus mv initial. Now, this only includes B now. Turns out that this force was pushed or created by the impact of A pushing on B to make it turn its direction. What was that? He said, what is the average impulse force? So that means you can pull this out and say sum of the forces And he said it occurs over a half a second. So this means delta t would equal to a half, or here, let me move this up one. Let me look on the stream and see if this is viewable. Yeah, this can be viewed. Yeah, this is good. Here. M B final minus M B initial. All I'm doing is taking this and copying up. Now I'm realizing what are the forces times delta T M B final minus the initial. The mass didn't change. It was 15. Okay, now here you have to keep respect of these directions. So you get a minus the final. This is the final. Okay, so here's your initial, here's your final. So take your final, 2, minus your initial. So, and this occurred over a half a second. So the average impact or average force that occurred, okay, so I need to include, okay, here, this 2, this ends up being 15, 3.5 over a half, or multiply that times 2. Shouldn't take me that long to do that. Hopefully, I'm going to make sure I clear it. Or 105. Now, this is an M, so this should be, when I say M, I mean mega here. So I carry the M through meganewtons. Usually I write TS, but that gets people confused. So I want to check this out. I want to check out this answer, and then that one, and this is 15.7. Let me write that down, and we'll spin forward. Wait a minute. F15.7. So I'm going to spin this forward. I hate to do this, but I'm going to do it and come back. This is page 259, where the original problem existed. I'm close. 15.7. There it is. Now I'm going to bounce the display back. Whoops. Wait a minute. Okay. So what you saw was our 3.75, and you saw our 105. So, in fact, we were good. Go back to 259. Oops, wait a minute. There we go. Oh, wrong button. There we go. So we got the answers correct in that. So the key is that the definition of the system. The system includes A and B during the impact. Nobody was pushing the thing during the impact. There are no external forces pushing or applying on the A-B system. If we redefine the system as only B or only A, we can work the system out from there. As an interesting side issue, let's do this. And I may just spend a few extra minutes here because this is some concept that comes in. Maybe we'll do that next time. The concept here off of this is, let's look at doing the system off of A. So this is with only A. Do we get a different answer here? This one should be, this one should be the force applied to B during the impact. Here we have A, which initially moves to the right at 3, and it tells you, wait a minute, is A moving to the right? A is moving to the right at 3. The A final is moving to the right at a very tiny rate, 0.375. If we come in here, sum of the forces times delta T, the final minus the initial. It's still a half second during impact. Let me make sure that the stream is picking up this part to the right. I think it goes to the edge of this dark section, so I think we'll just make sure we stay inside this dark section. Okay. The mass of A is 20. The final velocity of A, 0.375 to the right. The final velocity of, I'm sorry, I got that. This is the initial, and this is the final. No, I got that. That's 375 and 3. Now, if I did everything right, let's see what we got. .375 minus 3 times 20 divided by, and it sure enough becomes minus 105. Now, and this is meganewtons. Why is this one minus and why is this one plus? And of course, it would make sense that magnitude would be the same. And that is because during the impact, okay, let's look at this. During the impact, this is B only. The force was 105 meganewtons to the right. Over here on A, guess what? 105 meganewtons to the left. Remembering that we've set this up as being positive. So in fact, this, we did B, and it said in order for the velocity to change from going to the left to going back to the right, somebody had to push on it to the right, have it change its direction and go back that direction. It makes perfect sense. If it occurred over a half a second, that's the value. On A though, it's going this way. And of course, at the end of it, it is going still this way, but very slowly. So in other words, A is going this fast, after impact it's going this way. B, on the other hand, is going this way, after impact it's going that way. So it slowed, you took the velocity of 3 here, and you brought it to 0.375. You slowed it down. You obviously had to push to the left to slow this one down. So the answers make sense. The signs make sense. Let's talk a few more minutes about something. It's very hot in here, so I don't think I'm going to go the whole time because of the heat in here. But let's go back and take a look at where we're going next after this. Okay. And we'll just call it quits after this. I'll try to get back in here and work some more problems. Maybe it won't be so hot next time. So the next thing that happens is you have, so this is just laying things out. We have the possibility of 2 items impacting in such a way that they can move across a plane, much in the same way a pool ball on a pool table is. You know, you can have a line of contact here. There's a plane of contact right here. You have a line of impact. You could have 2 pool balls moving much in different directions and hitting each other somewhere on the table. It turns out, this is a good time to talk about this. Think about the 2 trains, A and B. They hit each other, they compress, they have a deformation impulse, then they deform a little bit, or quite a bit possibly, and then they restore or have a restitution value there. And then they have after impact. So you actually have what he's describing as 3 phases of impact. This one is occurring as an instant, but you have a deformation impulse and a restitution impulse. It turns out that, and maybe we'll come back to this exact problem next time, because what you have is during the compression, and then you can actually come up and show that there's a P. I can't select this, but maybe I can. No, I can't. Oh, there you go. There is a impact. He calls it a P. I'm not sure exactly why he calls it a P. It makes sense that the other one's called R, restitution, but here, let me check the stream and make sure you're seeing everything okay. Yeah, we're seeing everything okay. And so what you find out is, if you look at this, you have a P during 1. Okay, think about this. This was the train A. So this is just looking at train A. And this is, okay. And you look right here, just looking at train A as well during the restitution. What you have is these intermediate points. And he defines a ratio of the impulse of deformation, restitution to the deformation is called the coefficient of restitution. It turns out that this value can vary between 0 and 1. 1 being perfectly elastic, meaning the trains bounced off each other and didn't deform at all, which is possible, and the other being 0, in which they compressed together and they stuck together. And obviously the trains that we just saw did not do that. And then he defines this coefficient of restitution as the R, integral of the R over the P. Turns out you can look at train B and do a similar relationship, because you don't know the intermediate. Here's what I mean, you don't know the intermediate. You only know before impact, this information, and you know after impact. You're not really sure you know anything in between here, but it turns out you have 2 bodies happening here, this, and this one. So it turns out you can set your equation such that you can identify a behavior during this part. And that's what he's doing here. He says, oh, in a similar manner, if you look at train B, or particle B, you can write the R, integral of the R over P, and have these final, initial, and final. Now, the thing is his 1 and 2, 1 is initial, so it's bad. He has the 1 here, this being the initial, I called it I, and 2 being the final, I called that F. You divide them out, and lo and behold, you get an equation right here, coefficient of restitution. I guess we could sit there, and we got enough time, and I don't think I'll faint if I do this. So let's look at this. What is the coefficient of restitution during this impact? Remember, it has to be between 0 and 1. So let's write this down. Okay, I'm going to switch the camera in a second. E. And I'm going to adapt it for my subscript. Give me a second, and I'll switch the camera. Okay, let me switch the camera, and I may have to adapt some things here. Switching the camera. How do I do that? Okay. Wait. Is this it? Okay, there we are. And now what I need to do, we had our train here. Is that visible? Okay. That's in the way. I don't have my problem here. Let me do this. Okay. Okay, so let's just do this real quick. What's the coefficient of our impact? Coefficient of restitution. I took the equation and changed the 2 and the 1s to final and initial. By the way, you can flip this AB or BA, as long as you're doing them both denominator and numerator. E is equal to velocity B, final. This is B, that's A. Velocity B, final. Okay, you have to keep the signs. Velocity A, final. It's that one. Okay, so here's my, let me see here. These are my A's and my B, initial, final, initial, final. So I got a plus 2, final, plus 0.375, velocity A initial, 1.5, velocity B initial, minus 1.5. Whoa, wait a minute. I have that backwards. VA initial 3. VB initial. And I have no idea what that is. I don't know what the top is, if I did that right. And so I got this wrong. Something's wrong here. Okay. B final. F2. A final. 0.375. A initial. 3. B initial. Oh. B initial is a minus. 0.36. Make sure the thing is still going. All right, I'm done.